Hello, all of you. Welcome back to this series of lessons. When I was going through the syllabus for CPL and other pilot studies, etc., I found that one of the lessons is the solar system. So I decided to do a lesson on solar system and put. It was very interesting for me to go through these the solar system once again, and I've tried to package the lesson in a little bit more interesting manner. We will not be spending too much time in going through the nitty-gritties because it's mundane, and I'm sure we all did it in our younger classes. I will just skim through the most basic information. That is, the sun with the center of the solar system. We have about 9 planets. That is the Mercury, the Venus, the Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Now, I'm not going to cover the details of each planet in great detail. I will just merely point out some basic interesting facts to make the lesson more interesting. Otherwise, there's plenty of other resources available to gather information, and it has been put in our lesson as well. Okay, let's go through the first 2 planets, the Mercury and the Venus. Mercury is the smallest planet of the entire system, and its orbital period is about 88 Earth days, and it appears to move around its orbit in about 116 days. And all this is in terms of Earth days. That's what I wanted you to notice. And Venus is the second planet from the Sun, and it is orbiting uh, 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 the Sun every 224.7 Earth days, and it has got no natural satellites. And after the Moon, it is the brightest natural object in the night sky. This is the most lovable and the most interesting planet that the Earth, that's what we are living in. It was formed about 4.54 billion years ago, and it gravitationally interacts with the Sun and the Moon, and it rotates about its own axis 366.26 times in a year. And one of the very important features is its axis of rotation is tilted at 23.4 degrees from the perpendicular, and which is resulting in seasonal variations. And you all know that the Moon is the only Earth's permanent natural satellite, and the gravitational interaction from the Moon causes tides, etc. And over a period of time, it has been noticed the Earth's rotational rate is gradually slowing down. Okay, the Mars is the second smallest planet in the solar system after Mercury. The rotational period and seasonal cycles are similar to that of the Earth. Jupiter is the largest planet, and it's called the gas giant. And its atmosphere, as we study, appears to be very, very turbulent. Saturn is the second largest planet, and it's pale yellow in color due to its content of ammonia. And we have noticed severe electrical activity in the atmosphere of Saturn, and the wind speeds can reach up to 1,800 kilometers per hour. That's one whole lot of wind speed which can be perceived in our system. Uranus is the coldest planetary atmosphere in the solar system, with a minimum temperature of minus 224 degrees centigrade, and it has got a complex and layered cloud structure. Neptune is not visible to the unaided eye, and it's only the planet so far which has been predicted mathematical model predicted because of mathematical models rather than by empirical observation. This is very important. I thought I must let you know. Pluto, of course, some sections of our society don't consider it as a planet, but nevertheless, it's a dwarf planet and it's got high content of nitrogen, methane, ethylene, and acetylene. Okay, let us concentrate on our dear Earth. As I told you, Earth's axis of rotation is tilted 23.4 degrees away from the perpendicular. So, this is what is the main cause of seasonal variations on the Earth, which is very important. I'm sure you all will appreciate. So, I will take some time to explain this particular aspect. More definitions or facts. As we discussed, this all the planets go around the sun, which we call it center of the solar system, but not necessarily the physical center. It is the center, of course, but these planets go around in an almost like an elliptical orbit, and we will explain this particular thing a little bit more detail. Now, for a body orbiting the sun, the point of least distance at which during its orbit where it reaches is called the perihelion, and the point of the greatest distance is called aphelion. So I have shown in this diagram two positions of the Earth and the elliptical orbit, of course, uh, and all our planets also go around the I'm sorry, the satellites also go around the planets in not necessarily elliptical orbit, sorry, in not necessarily circular orbit, but elliptical orbit, and the points are called perigee and apogee, and as shown. So that's what is aphelion and perihelion. Okay, now we all know that sun is shining from one side, and the sunshine is received from one on the Earth's surface for one half of the surface, and the remaining half doesn't receive any sunlight, which is what we experience day and night alternately as the sun rotates. But the axis of rotation, as we discussed earlier, is tilted, and therefore it is going to give rise to other issues which I'm going to explain. So as to make this concept of tilt and its causes and effects more clear, so I thought I will take some more time graphics to explain that. Now here I've shown the sun in one extreme position with the tilt in a particular angle, and I have also blown up that particular diagram, and I want you to notice the portions which is not receiving the sunlight. Some portions are not receiving the sunlight at this point, even though with rotation. So that's what I wanted you to notice, and now I'm going to show different positions so as to make this point very clear. Okay, now I have shown the next position where the rotation axis has come perpendicular, and at some point during its rotational period it has assumed this position, and in this position the two sides of the Earth uh, which is coinciding along with the rotational axis, getting equal sunlight and dark portions. That's what I want to you all to notice. And those of you who are a little bit not with me, uh, it is an apparent movement of the sun which is taking place because of the earth's tilt. I want you to appreciate that. Here I have shown as if the earth itself is rotating and showing different positions. In actual, it is the apparent movement. Okay, in this diagram I have shown another extreme position where the tilt axis is well inside the sunshine areas, and I want you to notice the portions, places where it is receiving good sunshine, and what portions of the earth is remaining in the dark. This is also going to happen in some during some portion of the time of its rotational orbit. Notice this diagram. This is a position of the sun in one of the extreme positions. Obviously, it's not staying here forever. It reached on a particular day in this position. Right. So now the entire 24 hours of rotation, you will find that there are some places on the earth which will receive continuous sunlight. That means the entire day there is no sunset for those particular for in those one or few days in those particular places. So it's some places in the North Pole and the South Pole do experience. Similarly, there would be some days in which there is no sunrise. The entire 24 hours they are experiencing night, no sunshine. As I mentioned to you, all the planets go around the sun in an elliptical orbit. It's got a lot of significance, and we have to recall what is the definition and the properties of ellipse. And I think ellipse is a very, very important, very important shape, you can say. It's we should understand, and it's the extension of circle, of course, but we must understand what is an ellipse and how it affects the motion and different phenomena. This very tilt of the Earth's rotational axis, and causing the apparent movement in the sun's position, is causing several other phenomena, which I'm going to explain. First is equinox and solstice. An equinox is an astronomical event in which the plane of the equator, Earth's equator, passes through the center of the sun, making night and day approximately equal length all over the planet. Obviously, this is the rotational axis. Equinoxes occur twice a year, around 21st March and 23rd September. Whereas solstice is an astronomical event that occurs twice a year, that is 20th June and 21st December, where we experience the longest day of the year and the shortest day of the year, and they are called summer solstice and winter solstice. And all these four dates mark beginning of or transition of seasons on the earth. Okay, now we are at the study of planets, so I thought it is important to cover this Kepler's laws of planetary motion. Though they say now Kepler's laws are not very well accepted in some quarters, nevertheless, I think they formed a very strong fundamental knowledge and basis for a lot of other further studies. He himself worked for several years and gathered several years of data done by his predecessors, and then came out with these laws. So we will go through them. I'm just going to introduce them cursory. The path of the planets about the sun is elliptical in shape, with the center of the sun being located in one of the focus. An ellipse, incidentally, has got two foci, you can say, and that's what is Kepler's first law, that it is follows an elliptical orbit. Okay, maybe that was pure theoretical. Let me explain it a little bit more mathematical. In this diagram, I have shown an ellipse and sun in one of the positions of the foci. As we told, an ellipse has got two focal points. Now here x and x dash are those focal points, and sun is located in one of the apexes of the ellipse. Now I have shown the position of the earth in three different places in the orbit, that is A, B and C. Now let's see how it follows the rules. The distance x dash A plus ax, that is the distance between from on a point on the ellipse, on the orbit as occupied by now here in this by earth in this position A, that means distance x A and x dash A, the sum of it is equal to let's take position of the earth at B, little bit to the left and far away, that is x dash B plus bx equals x dash C plus xc. That means the sum of these distances from the focal points to the point on the orbit will always remain same. That's what the definition of ellipse would mean, and that's what the Earth and other planets, that's the rule which they follow while going around the elliptical orbit around the sun. Let's get on to the next law, called the law of equal areas. An imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. That means this is another aspect which we will need to explain in a little bit more detail. Okay, let us consider two sections of Earth movement on its orbit. Here I have shown one is the section from position A to position B, and the other one is section from position C to position D. Now A to B it takes T1 time, C to D it takes T1 time. Obviously T1 is equal to T2. That's what the definition says. In equal time, it sweeps equal areas. That means the areas of triangle AXB, ABX, whatever you call it, and the area of CXD or CDX, these two areas remain same. That's what is meaning by this particular law. Okay, the third law is called the law of harmonies. The first two laws are concerned with the planetary movement and its definition on standalone basis. Here, he tried to define as to how these different planets have correlated movements. Let's go through the law per se. The ratio of squares of periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. Now, What is a period? Period is the time which it takes to go around the sun in once. That's what is called period. And average distances, of course, you know. Now this, the time which it takes go around the sun once and reach back its original position, of course, it is calibrated in terms of earthly years or in seconds or minutes, whatever is the standard time. So this is how the interrelated planetary motions are linked. Okay, we talked about astronomical units, which we said that all timings are comparable to that. Timings and distances, of course, are comparable compared with that of the Earth to Sun. So I tried to show it here. The average time period in which the Earth goes around the Sun is 3.156 into 10 to the power 7 seconds. That is one astronomical time unit. And average distance is 1.4957 into 10 to the power 11 meters. That is the average astronomical distance unit. So, so twice will mean twice this particular distance is called, and that is how the astronomical units are defined. Here in this table, I have tried to show two cases. First is Earth and Mars. I have tried to compare. Now, period in seconds, as you can see, Earth takes 3.156 into 10 to the power 7, and Mars takes 5.93 into 10 to the power 7 seconds. And of course, there is a distance, which average distance, which is there. So, the ratio which we talked about, the period square into average distance cube, the ratio is almost same. As you can see here, it works out to 2.9 into 10 to the power minus 19. That's what is there. Now let's go down, and I've taken two more planets, that is the Mercury and the Uranus. Now here the time period has been converted into years. That means Mercury is 0.241, which means that it takes 0.241 years of Earth's time, and Uranus takes 84 years of Earth's time to go around once. That is the period of Uranus. And of course, there is an average distance. Average distance is 0.39 times as that of the Earth, which is for Mercury. Now again, if you were to take the ratio of the cube and t square and r cube, it works out to 0.98 or 1 approximately, and you can so it is universal. It is that's what the rule states. Now that we are here, I thought I must introduce you to this Newton's law of gravitation, which I think it's very important, and we are going to cover it in future as well. But nevertheless, when we are in a study on solar system is never complete without the mention of gravitational forces. So every particle attracts another particle with a gravitational force whose magnitude is as given, which is proportional to the respective masses and inversely proportional to the square of the distances. So if I were to replace the proportionality with a constant, the formula works out to F equal to G into M1 into M2 divided by R square, where G is the gravitational constant and M1 or M2 are the masses of the individual objects, and R is the distance between these two objects. And the gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square upon kilogram square. So this is very interesting and important, and we will be covering it in another lesson. I thank you all for going through this lesson, and I hope you enjoyed this, even though it's a little bit dull, so I tried to get some facts and some good graphics so that it will make the presentation a little bit more interesting. Anyway, please feel free to offer your comments and keep following my lessons in YouTube and on my website. Thank you all once again.